computer. And let's share the screen again. I want to share this desktop one. Yeah. Can you see my slides? Great. Thanks for the feedback, because it wasn't showing me the slide, it was showing me the actual desktop, what is behind this. Okay, so, yeah. Okay, the last one, one of the last ones, I don't know if the last one, is going to be osmosis. So osmosis is when you have a semi-permeable membrane. What is a semi-permeable membrane? It's a membrane that actually lets only certain compounds or molecules or ions go through. And so semi-permeable membranes is what actually keep us alive, meaning that cell membranes, for example, are semi-permeable membranes. So they don't allow everything to come in, otherwise, or everything to come out. Otherwise, all our cells will be in equilibrium with our environment. First, we need to live in water, and second, the water that will surround us will have to have exactly the desired concentration of ions, and that is not the case. We don't live in water, and even if we have water, it's not in the desirable concentration. One of the things that you probably have experienced is when you put your hands in water for a long time, they kind of wrinkle, the skin wrinkles, and that is because water is going in and out of, is going actually into the cells. So that is called osmotic pressure, and there is a force that will drive the passage of molecules. In this case, it's simple to think about water. It's going to allow the osmotic pressure will allow the molecules of water to travel through the semi-permeable membrane, whether it's in your cells or is it a synthetic membrane, like in reverse osmosis. You probably have heard that for the purification of water. Some towns and countries actually that they have very little water, they can actually take seawater and use reverse osmosis to produce water, potable water, drinkable water. Okay, so the equation that we're going to use for that is going to actually resemble a little bit the gas phase and the delta T that we have been using. So here we have the Van Hoff factor, I. The second one is going to be the molarity now. That's the molality, but the molarity, and that's capital M. And then R is going to be the gas constant, and T is going to be the temperature. Remember, when you use T in your equations, the T needs to be in degrees Kelvin. So make sure that you don't make that mistake of using degrees centigrades. Okay, so for example, if we look at the red blood cells in our body, they have the same osmotic pressure inside the red blood cells as there is outside the red blood cells, which will be the blood or the plasma in our blood. So that needs to be maintained. So when you actually put an IV, whether it's a salt IV or a sugar or glucose IV, that IV has to have exactly the same osmotic pressure as the solution, as your plasma, and as the plasma that is in your blood. Otherwise, if it's different, it's going to affect the osmotic pressure of your blood, and your blood cells will either collapse because the water is going to come out, or the water comes in the other way, so it's not going to be at equilibrium, and the cells get swollen first, and then they burst open, and then you kill. In either way, you affect the red blood cells. So that's one of the applications of osmotic pressure. So when they prepare those solutions, we know what the osmotic pressure of our blood is, and so therefore it has to be the same. The other way that we're going to think about osmotic pressure is when we are talking about desalinization of water. That means taking ocean water and make it potable water or drinkable water. You need to apply a pressure to the seawater and you have to have a specialized membrane that they were developed in the last 30 years and improved in the last maybe 15 years to be able to make possible to be able to desalinate water, ocean water in large scales. So it's a membrane that allows only molecules of water to go through. Ions will not go through, sugars will not go through, bacteria will not go through, nothing goes through but water. So when you push imagine a filter paper or filter paper, and then you put water on top of the filter paper, the water creates a pressure on the top of the filter paper and pushes the water through. Gravity, we'll say gravity pushes the water through. When you have a membrane, like an osmotic membrane, to do osmosis, you have a membrane that is permeable to water, and therefore you need to apply pressure on one side to be able to drive the water across. So in the case of desalinization, we're going to increase the pressure on the seawater. How much do we have to increase the pressure? We have to increase the pressure to actually affect or overcome the osmotic pressure of the solution. The osmotic pressure of the solution is going to allow, actually, if you put a membrane, semi-permeable membrane that allows water to go through, you put pure water on one side and seawater on the other side. What you're going to see is that there is the concentration of water molecules on the pure water is going to be larger than the concentration of the water molecules in the ocean water. Why? Because the ocean water will not only contain water, although it's most of it, it contains ions and other things. So if you think about the concentration, how many there are going to be, how many molecules of water there are going to be per unit of volume, there's going to be less molecules of water because inside that volume is going to be other things. And therefore the concentration is less. So what you're going to find out is that the water in the pure water is going to start migrating towards the seawater. Now, that's contrary to what we want. If we want to actually take seawater and make potable water or pure water, we need to go the other way around. So we need to overcome that flow. And so to overcome that flow, we need to apply pressure on the seawater side. By applying pressure, actually physical pressure, with a pump and pressurizing it, we have to overcome that flow. So that's why it's called reverse osmosis, because the osmosis naturally will be the water going into the seawater. Since we want to do the reverse, so that's called reverse osmosis, and the seawater then the water molecules in the seawater, by applying at least the osmotic pressure of the ocean water, is going to go into the pure water side. Let me see if they have pictures in here. This is the red cells I was talking about. So the term is isotonic. So those IVs, they're called, since they have the same osmotic pressure, they're iso means same, tonic means strength. So they have the same strength as the plasma, and the plasma has the same strength as the red blood cell. So this is a healthy blood cell. Here is a blood cell that actually has lost water. If you put too much concentration of sodium chloride or glucose in that IV, what it's going to do is the concentration of water molecules outside the cell is going to be less than the inside of the cell. And the water is going to travel from the inside towards the outside. And therefore, you're going to see that the red cells collapse. Okay, so the water is going out and they shrink. As you can see, these are smaller than those. And what happens when you put too little? Then you're going to see that the water from out, there's more water on the outside than there is in the inside of the cell. So the water is coming into the cell. So as the water comes into the cell, it makes a balloon like this and eventually break down, because there's going to be so much water that actually literally it explodes. The membrane breaks down. Okay. So here's this semi-permeable membrane. This is for reverse osmosis or at the molecular level in the laboratory, not in the blood cells. So here you have the sodium chloride solution, and here you have seawater. Now notice that the seawater has a concentration of sodium chloride equal to 1.15, and this concentration is 0.10. So where is there more water? In the 0.10 or in the 0.15? Now remember that 0.10 and 0.15 represent the concentration of the solute. The water is the solvent. So there is going to be more water on this side, since there is a lesser concentration of ions, and this is represented by having put less ions here, more ions here. So what is going to happen is going to be the water molecules are going to collide and to the membrane, and they're going to travel through the membrane and going into the seawater. Some of the water in the seawater is going to also collide with the membrane and go towards the sodium chloride, the 0.10. But there is going to, since there is more molecules of water on this side, there's going to be more of these. So those are represented by these blue arrows here. So there's more flow towards the more concentrated solution than towards the least concentration solution. There's only one arrow going that way. So again, this is an equilibrium. So the molecules of water are traveling in both directions, but there is more flow in one direction than the other. So do you expect this volume to remain constant, to go up, or go down? Who can tell me what's going to happen now that we have discussed the movement of water molecules? What is going to happen? My question is, what is going to happen to the seawater level in this tube here?
Go up, right?
It will what? I'm sorry.
Go up, because the rate of water going to the left sides should be higher.
Yes, you're correct. There is more water going towards the left-hand side. So that is exemplified by this arrow. That's the net. And therefore, as the water goes in, it's going to dilute the seawater and the volume is going to increase. So we can expect this volume to increase and this volume to decrease. And this occurs naturally. We don't have to do anything to it. As long as we have the right membrane that only allows the molecules of water to go through, we're going to observe that. Now, to be able to prevent it, we can put a plunger here. Let's see, let me draw a plunger. There's the plunger, and let's make it a stick so we can handle it. And we're going to push down on this plunger. If we push down on this plunger, then we're going to create a larger pressure here. And that pressure is going to allow this, instead of being one, there to be 3 arrows going the other directions, which means that now at the osmotic pressure, when we have the pressure equal to the osmotic pressure of this, the difference in the osmotic pressure of these two solutions, we're not going to observe at any displacement of water, because the water is going to be going at the same rate to the left as it is going to the right. So that is the reason why this is called osmotic pressure. So, okay, questions? So will this seawater, again, the next question, and now I see this one, this seawater is 0.10, correct? And if the water is moving this way, if the water is moving this way, what is going to happen to the concentration of sodium chloride? The sodium chlorides are not going through, which means that the volume is going to decrease, but the amount of sodium chloride is going to be the same. So if the amount of sodium chloride stays the same and the volume decreases, then the concentration is going to increase. When the water goes this way, it's going to dissolve more, or it's going to dilute this concentration. So this concentration is going to go down. So one concentration goes up and the other concentration goes down until they're not that far really, until somewhere in the middle, they're going to meet and they're going to be equal. When the concentrations become equal on the left and on the right, that means that the equilibrium has been reached and there is a balance between the amount of molecules that go to the right and the amount of molecules that go to the left. And that only happens if the concentrations are the same. So having said that, what if this would have been just pure water? When will the osmotic, when will this process stop? Anyone? Yes? The osmotic, if this is pure water, if this would be pure water, the osmotic pressure will be 0 because there is no solute, right? It has to be the, so this osmotic pressure is going to be 0 and this is going to be some kind of osmotic pressure because there is going to be solute. As the water travels through in this direction, it's going to dilute it, but it's never going to go to 0. So theoretically, all the water here will go onto the other side. Why? Because the osmotic pressure is going to be higher on this side. So, okay. So this is what is called reverse osmosis, and it's not usually like this. Nowadays the design has changed, but it serves okay. It works okay. So these are thin tubes that are inside another tube, and the pink material is the membrane. And so by applying pressure on the seawater side, so the seawater is on the outside, you're going to start moving molecules towards the inside of this tube. Since the membrane only allows water to travel through, then you're going to start collecting water here, and this water is going to travel downwards by gravity into the exit of the reverse osmosis process. And so you're going to have a flow of pure water coming through those tubes. The water here is going to become more concentrated, and therefore it's going to take more pressure to send through. So usually what they usually do is inside this gray tube, on the outside or in the space between the tubes, they have the seawater. And they don't have it static, they have a slow but steady flow of seawater. So as the water molecules go into the tube, they don't need to increase the pressure. The pressure is going to the pressure is going to be high enough for all the surface all along the tube to be able to let the water molecules in, and not any other thing, none of the solutes. And that's how it's used as desalination or for desalination. Okay, what time is it? Oh, I think it's time to stop, right? I should have stopped. Let me see, 8:30, 9:30, 10:20. Oh no, it's not 10:20. Okay, so let me stop the recording. Let me see if it allows me to do that. Yeah, stop recording.